So we are now starting into chapter 3 in our textbook about the Schrodinger equation and the particle in a box. So this is really the fundamental basis of quantum mechanics. So we talked about how de Broglie postulated that matter can act as waves. And so if matter acts as a wave, just as we saw in the previous chapter, with classical objects, a normal macroscopic object like a string, we have a wave equation that describes that string and how it behaves and how it evolves over time. And so if matter acts as a wave, there must be some sort of quantum wave equation that describes how the matter acts when it shows wave-like properties. And so the basic idea of this quantum wave equation was posited by Schrodinger. And so his equation is really the equation that underlies all of quantum mechanics. And so, all the properties that we find out about quantum mechanical objects really come from solving the Schrodinger equation, finding what these, what describes this wave behavior of matter. And so in short, the Schrodinger equation can be written as this: H psi equals E psi. Now, there's a lot built into that. There's a lot of assumptions involved here. And not assumptions, but definitions, I should say. So first we'll talk about this H over here. So this is what's known as the Hamiltonian operator. And it takes the form, if we're looking at a one-dimensional problem where we're not worrying about time. So time independent. So if we were, say, in the classical example, if we just looked at the x part, right, and we ignored how things change over time, we can look at how the time dependence of this as well, and there's a time dependent Schrodinger equation, but we're not going to worry about that in this class. Keep things simple, relatively speaking. And so the h here looks like this: negative h bar squared over 2m. Second derivative with respect to x being our one dimension, our variable, plus some form of potential energy. And so that's the h. The psi here, this is what we call the wave function, and this is the Greek letter psi that's generally used to represent a wave function. And we'll talk more about what exactly a wave function is. Not completely. It's what exactly a wave function is a matter of significant philosophical debate in the physics community. But we'll talk about what it represents in terms of what we can understand about particles and what the wave function can tell us. And then E here is our energies of the system. And so when we're looking at the Schrodinger equation, usually we define the Hamiltonian operator. And in particular, this potential energy term is what varies a lot from problem to problem. And what we're usually trying to get at are what are the energies of the system. So this is an output. We're trying to find out what are the energies of the system, and also what are the wave functions, which tells us about some of the properties of our system. So in this chapter, we're going to introduce some of the ideas that we need to understand the Schrodinger equation. For one, why is there this little hat here? That represents an operator, which we'll talk about next. And then we're going to apply the Schrodinger equation to a specific example that we call the particle in a box. And this is an idealized system, not terribly realistic for a real chemical system, but it's an idealized system that we use to introduce many of the ideas that show up in other systems that we do care about more. And the particle in the box can act as a model for some simple circumstances, such as an electron in a conjugated carbon system. And that's actually, we'll use that as an example in in our second lab that we do this semester. So this is our brief introduction to the Schrodinger equation. We'll go into all of this in more detail. But our next video, we'll talk about operators and what operators are and how we use them.